My name is Ernesto Chaves. I'm a network engineer at AppNexus, working for the past 5 years. And before diving in, I had a question. How many of you guys currently use F5 load balancers in production? Oh, that's quite a lot. I wasn't expecting that. So, about AppNexus. We got recently acquired by AT&T, so we're now part of Xander. First and foremost, we are a technology company. We provide programmatic buying and selling of digital advertisement. I mean, there is Facebook and Google, the big boys. They're in the same business, but we are different. We provide a transparent and open exchange. We also have a platform that brings together people who want to buy advertising space and who want to sell advertising space. Having said that, so load balancing. What does load balancing really mean? So I leave here a broad Wikipedia definition. Most of you guys know what it means, but we as a technology company, we run a lot of business critical applications and services. So we need reliability, we need availability. We cannot rely on a single component. We need to be able to optimize resource use. We need to be able to minimize response time for the end users. Software versus hardware-based load balancing. Both approaches increase reliability and capacity by distributing the traffic across multiple servers. Software-based solutions use the main CPU to handle the traffic. Hardware-based solutions use dedicated hardware or devices to offload that traffic onto. Those devices can be ASICs, FPGAs, processors, etc. Back in 2009, we decided to go with F5, when we were a cloud computing company, and those devices were deployed in a pure layer 2 network environment, serving core services and applications. And they could be internal or external facing. We also have a layer 3 network environment where we run high volume applications. So these were the services that used the F5 solution. Most of those services you might already have heard of, others not so much. But keep in mind we have specific application services that we developed internally for our customers' use. About the F5 architecture, I'm leaving here some key characteristics. We deployed the F5s in 5 data centers: New York, Los Angeles, Amsterdam, Frankfurt, and Singapore, with clusters in active standby fashion. We had a lot of virtual servers, nodes, VLANs, and SFIPs. We also run BGP and spanning tree protocol on those devices. And I'm also leaving here some key traffic statistics so you guys can have an idea of how active those devices were at peak. So this is a high-level network diagram of the F5s. And here, they were basically connected to the core switches. And those core switches are connected to edge routers. And then the edge routers are connected to the ISPs. And we run MSTP and VRP for gateway redundancy purposes. And we run, one side is the root bridge and VRP master, and the other side is the backup root bridge and VRP backup. We also run BGP between the core switches and the edge routers, and we run BGP between the F5s and the core switches. As I mentioned earlier, the F5s were deployed in active standby fashion. So only the active node will balance traffic to the backend servers, and we have the pools of backend servers hosting the end user applications here on the bottom. This is a more detailed network diagram. So there is a subnet, for example, that is configured on the core switches that belongs to a public IP space that is going to be advertised to the internet, from the core switches to the edge routers, and then from the edge routers to the ISPs. On that public subnet, we have self and floating IPs and configured, and we have also self and floating IPs configured on the backend VLANs and subnets. On that public subnet, we have also defined virtual servers or VIPs that are going to be reachable from the outside world. So traffic will hit those VIPs, and then the F5s will do some magic to load balance traffic to the backend nodes. So this is a basic usage of the F5 load balancing architecture. So we had management tools that helped our customers and internal users manage their pools. They were basically CLI commands, right? Developed internally, and the standard user, they didn't have access to the F5 CLI, and of course those commands had to be supported on the new NGINX solution. So let's talk about what went wrong in our case with F5. So F5 at AppNexus was a good solution when we were a small company with different needs in terms of traffic and applications. As we grew, scalability and reliability concerns became really a priority as more and more applications were being deployed behind the F5s. So we started seeing a lot of performance issues, high CPU utilization issues due to an increase in traffic. The plans were not stable. We spent hours troubleshooting, opening cases, so on and so forth. These specific problems that we saw, specs not matching real usage, SSL limitations, memory leaks and core events, demons or chassis rebooting randomly, split brain scenarios, and others. So this is a timeline of the issues that we saw with the F5s, and during the span of 4 years, and of course I'm not representing here what happened before my time at AppNexus, before 2013. So you guys can have an idea how painful and difficult this experience was with F5s. So this is a picture I took when we went to see our friends at F5. And we sat down with them with some technical and sales folks, and we explained all the issues that we were running into. And towards the end of the meeting, they came up with this insane and impractical idea of deploying layers of F5 to address our performance issues. As you guys can see here in the middle, this is what they were proposing. So basically what they were saying is, you guys need to deploy more hardware. So they basically were throwing more hardware at the problem in hand. And this was our reaction looking at that diagram. So specifically, this was what they were proposing. So layers of 5250s and 4200s. And the new architecture had to be deployed in at least 3 data centers because they were problematic. There was no guarantee in terms of gaining performance. It would have increased the physical and power footprint. More devices need to be supported, more single point of failures in our network, etc. And the solution was also expensive, over $1 million per data center. Regarding the roadmap, there was a lack of visibility long-term as to when the next gen of F5s with Cavium 5 processors would have been available. They said that we need to wait for at least 18 months. So we couldn't wait. So we looked at alternatives, and these were the requirements that we laid out. The solution had to prove high performance for high volume of non-encrypted and encrypted traffic. The solution had to be resilient in case of failure. It had to be manageable through an API, software and hardware upgrades. They had to be transparent from the end user perspective. The solution had to be able to scale. The solution had to be less expensive than the solution that F5 was proposing. The migration process had to have a minimal impact in production, and we don't want to have any regression in terms of features that were already being used in production. So why NGINX Plus? That's a good question. These were the reasons why we chose NGINX Plus. So they responded to the above requirements with some caveats. We are really looking at Intel Quick Assist technology. We were already running NGINX Plus load balancers in our layer 3 network environment. So there was an existing technical and operational knowledge about F5. We had a good business relationship with them. And any NGINX server-based solution would have been less expensive than any other hardware-based solution. So when we were setting the requirements for the alternative solution, we were interested in having, initial offloading because we wanted to reduce the burden of those SSL operations on the host CPU, and we were seeing an increase in SSL traffic. So we looked around and reached out to Silicon, who at the time was selling rebranded Intel QAT cards, and those cards were already available and inexpensive. We also reached out to Cavium, but their Nitrox 5 processors were not yet available, and they turned out to be more expensive. Here there is a typo, it's supposed to be Nitrox. Sorry about that. I'm not going to talk much about the Intel Quick 6 technology, what it does, because there is a lot of documentation online. I'm leaving here a link so you guys can check it out. But we were interested in its crypto capabilities because we wanted to really reduce, like I said, because we were seeing a lot of SSL benchmarks online showing good performances. So we wanted to make sure that was the case. So we decided to run around benchmarks. So this is a lab environment that we set up with Dell servers, Intel QAT cards with their respective drivers, asynchronous OpenSSL, NGINX open source, some Erlang solution to generate a large number of SSL traffic, and web servers in the backend. So this is just what I just described. You know, web clients sending a lot of SSL traffic to the load balancer, and on the load balancer we have installed the QAT card. The NGINX load balancer will listen to 2 different ports, and on the right we have our web servers. So this is the interesting part of this presentation. This is some of the results of our benchmarks showing software versus hardware performances. And as a performance, I mean average CPU utilization in percentage. The lower, the better, right? And that also translates into higher or lower SSL rates. As you guys can see here, as we increase the number of connections per second, the average CPU utilization on those boxes increased dramatically, reaching a point where all the CPU cores were pegged at 100%. On the other hand, using hardware acceleration, we could save a lot of CPU cycles, hence better performance with higher SSL rates. And this is just showing these 2 cipher suites, but we run the same benchmarks on all the cipher suites, and the results were similar. So this was one of the setbacks that we encountered during this project, which was the lack of NGINX Plus support for QAT. And this was the official NGINX response for it. So Intel and OpenSSL were working on asynchronous OpenSSL 1.1. I believe they're still working on it. That was not yet available. Intel and NGINX were collaborating on extensions to NGINX Plus to support the Intel QAT cards, but there was no timeline as to when the integration would have happened. So we started pushing for an experimental build, but we couldn't wait. We kept running into the same high CPU problems on the F5s, and at that time the QAT cards became optional. So the 5 load balancing solution had to be broken up into smaller pieces or architectures because it was impossible to migrate everything into a pure single NGINX Plus architecture. So the first one allowed us to migrate 90% of the existing pools. The second one, we were really leaning towards isolating this DNS and ECAS service because it was really critical even before this project started. And the NAT capabilities couldn't be implemented on the NGINX load balancer, so it had to be a separate and different type of cluster. So this is how we set up the NGINX Plus servers, clusters of n numbers of servers deployed according to the current traffic needs in active fashion, NGINX configuration files for each virtual server and pool. IPLS is configured at the OS level for each VIP. And here what is new is that we used BGP for BGP dynamic routing to advertise those VIPs to the core switches. We also have a service that is actively checking the status of each pool, withdrawing or re-advertising those VIPs. The monitoring here is done via NGINX API and cache point tests, and the deployment costs were around $132,000 for this specific architecture. So this is how the NGINX Plus Layer 3 architecture looks like today. So there are, servers on top running an NGINX Plus and advertising those VIPs to the core switches. Those VIPs are contributing /32 prefixes to route aggregates that we configured on the core switches. Those route aggregates is going to be advertised to their upstream devices, and those upstream devices would then advertise those /24s to the ISPs. So the end user can reach those services and applications behind the NGINX load balancers from the internet. So the deployment of the NGINX NECAS architecture was pretty straightforward. Clusters active of 2 to 3 servers per data center. NGINX configurations file for each virtual server and pool. Here we used limit con zone and limit con to limit the number of connections that we can have per single IP address. The rest is pretty much the same as we saw on the previous architecture. Deployment cost here was around 0 because we were using VMs. This is the same principle, using VIPs and route aggregates. Nothing new here. So as mentioned earlier, we're seeing an increase in SSL traffic, and more websites started using more and more HTTPS, and we were seeing a large number of mobile devices accessing those applications. And as you guys know, the public certificate key sizes and the speed of operations on those devices are really predominant. So we started looking at elliptic curve cryptography because the certificates have a smaller public key sizes. As you guys know, NEC certificate of prime 256 bits will offer better security than an RSA 2K bit certificate that we were using in production. This is just a couple of OpenSSL speed tests that we ran, showing how fast the ECDSA signature operations are compared with the RSA ones. It's just a lab that we set up for this. We had to purchase this certificate, DCC certificate, because we didn't have one. This is the testing architecture. Here, the only thing that we did new here is that we configure this load balancer with dual certificate support. And here are some of the results for CPU idle in percentage for different cipher suites. We can see that we can get better performances if we use ECDSA cipher suites. For instance, when we are starting at 10,000 requests per second, for RSA cipher suites, we were around 90% CPU utilization, reaching a point we couldn't run more tests afterwards. For ECDSA cipher suites, on the other hand, we were around 50% CPU utilization, and we slowly went down to 40% as the request rate increased to 16K. This is just a graph showing the performance gaps between these two types of cryptography. So conclusions, the results showed how much CPU cycles can be saved using ECDSA ciphers. So back in November 2017, we decided to go ahead and deploy this feature in production. And just as a side note, we have to upgrade all our servers to Ubuntu 16.04. Otherwise, this wouldn't be possible. So as you guys remember, we started pushing for an NGINX Plus experimental build with QAT support. Back in February 2017, we finally received it with a procedure, but the results were not that good. We ran into some issues setting it up, and Intel helped us figure out what was happening, and we finally then proceeded to evaluate the cell performance of this. So, what is new is that instead of using Sun and Erlang here to generate a large number of connections, SSL connections, we use Python and Bash scripts to generate a large number of SSL connections, and we also used IP aliases to source those connections. So this is the lab that we set up. Nothing new. On the left, the web client sending a lot of SSL traffic to our load balancer here. This load balancer is configured with this, it's set up with this experimental build, and we have the QAT card installed on that load balancer, and we have our backend server on the right. Here are some of the results. Green is good, red is bad. What we can see is that for RSA cipher suite, there is a real benefit of using hardware acceleration. For ECDSA cipher suite, here on the bottom, not so much. The results show that we can achieve reasonable CPU savings with the QAT solution for RSA ciphers. For ECDSA ciphers, there is no benefit of using the QAT solution, as the performances are pretty similar, and in some cases even worse in hardware. So at the time we didn't know, and we want to understand why we're seeing those differences in terms of performance. So we asked around, and NGINX confirmed that behavior. We also reached out to Intel, and they came back with this reasonable explanation that we could match and exceed the QAT performance if we use a relatively high number of CPU cores. For the reasons above and the lack of support, because this was not a fully baked NGINX Plus version, we decided to drop the QAT solution. So back in October 2017, we were happy migrating all our pools from Dev 5 to the NGINX load balancers. And we started migrating one of our major customers' pools to the NGINXs. And during that process, at one point, we noticed that the request rate dropped immediately without any reasonable explanation. So we had to roll back. And we started a technical investigation as to why that had happened. So everyone knows what HTTP persistence is. Here the idea is to have multiple HTTP requests and responses over the same TCP connections. There are some differences between HTTP 1.0 and HTTP 1.1 that everybody's aware of. And this is how the HTTP persistence worked with F5. So it didn't matter which HTTP protocol version we were using, there were always persistent TCP connections on the backend. For the NGINX load balancers, on the other hand, we were not seeing any persistence on the backend at all. And the main difference between these two models is that F5 will always maintain persistent TCP connections on the backend, overriding the connection header if necessary. Then NGINX will always send by default connection close, even if we were using HTTP 1.1, preventing the TCP connections from being reused on the backend. So during our investigation, we took a lot of packet captures at peak and off peak, and we noticed that our customers were extensively parallelizing their HTTP requests. So the idea was then to prove that the lack of keep alive support on the backend, of the lack of persistence on the backend, was to blame. Real HTTP data was used and replayed using Python scripts in order to simulate the same behavior that our customer was seeing on their end. So these were the TCP streams that we saw using Wireshark conversation analysis, showing how many packets were being sent over the same TCP connections and the duration of those connections. I mean, those numbers are pretty significant. We weren't expecting those numbers. So this is how we set up the labs, internally and externally. Nothing new and exciting here. And these were the number of requests per second effectively seen when we launched the script at 20,000 and 30,000 requests per second. And as you guys can see here in the blue line, the request rate dropped immediately as the number of requests sent over the same sessions increased. And the same was seen at 30,000 requests per second. So conclusions, keep alive support is on the back end is as important as it is on the front end. Back in December 2017, we sent a technical report to our customer. Our customer accepted the root cause and fix, and we then restart the migration of their pools. So this is a timeline of the whole migration. So we started in mid-2015, and we completed the migration in February 2018. So what's next? WAF, rate limiting, HTTP2 is certificate. Here the sticking point is really HTTP2, which we had to roll back because of this. I mean, it's really hard to troubleshoot then, but the problem here is that we need to have time to troubleshoot this specific issue, right? To reproduce it in your lab, etc. And I believe we are done upgrading all our servers to Ubuntu 16.04. So summary. F5s had lower performance compared with the NGINX load balancers. We ran into some stability and limitation issues with the F5s. The F5s didn't scale. In our case, we have today better operational technical knowledge with NGINX Plus load balancers that we had with F5 previously. The proposed F5 solutions were more expensive than the NGINXs. Here are the figures. And we had some setbacks along the way with the lack of NGINX Plus support for QAT. And there were some operational and technical hiccups during the migration that had some impacts in production, but those impacts were limited and promptly resolved. I think this is it for me. I just wanted to thank all these folks that were involved in this project. And now I'll be more than happy to respond to some questions. Yeah, sure.
Did you look at what kind of server and CPU cores would be most efficient as opposed to like cheaper, buy more cheaper servers with smaller number of cores versus more expensive servers with larger number of cores? And what did you end up getting?
We end up getting Dell 6220s, and that's the models that we have. And we did compare different performances between and the more cores we had, of course, we had better performances. Yeah, but we ended up using 6220s. And in terms of the number of servers that we deployed compared with the number of plans that we had, I mean, the relationship was really one-to-one. There was not really a big difference there. Yes, please.
Were you virtualizing the NGINXs, or were you running them there at all?
Yes, we did for the DNS Anycast architecture. I believe there are some data centers we did virtualize for the default cluster. So we had three architectures that we deployed. The default one that allowed us to migrate 90% of our pools. For that one, I believe 90% of the load balancers are bare metals. And I believe maybe 10%, 5%, I might be wrong. We virtualized, but for DNS Anycast architecture, it's fully virtualized.
So did you notice any performance differences?
Not really, because as we see the traffic increase, we can scale in terms of number of appliances, number of virtual servers that we will need to deploy. So that's what's pretty straightforward. Yes.
During the rest of the software performance tests, were the clients resuming previous SSL sessions, or I imagine were they fully implemented?
So the resumption was something that we disabled initially on the F5s, and I believe we enabled on the NGINX load balancers, but from our tests, we weren't using any SSL resumption. So every connection was one SSL handshake, different from the next. There was no reusing of the tickets and all the good stuff that we can use on SSL to optimize the performance. Because what we wanted to stress is how efficient the NGINX load balancer, on this case, the QAT cards or the benchmark comparison between ACDSA and RSA benchmarks, where we didn't want to have any other variable in the middle. So we wanted to use a simple first handshake and come back with a result, a simple request, and compare the performances between these two types of models. More questions? Yes.
The F5 configurations that you had, were they running any iRules or something similar that you also migrate?
Yes, they were running. I mean, we had a lot of iRules, and they had to be because there were specific cases where we had iRule custom configurations for some pools that we had to they had to be taken care of when we migrated to the NGINX Plus. But I mean, the migration was pretty straightforward. It was not, but we were using iRules, yes. Yes.
Did you run into any pushback from any other team members or other teams in the organization about, well, why are you switching from software?
Not really. I mean, the most important part here is that we needed to maintain the same, operational and continuous functionality of all the things that people had on the fives. As long as they had that in place on the NGINXs, they were okay with it. Yes, please.
Did you do any testing with F5 software solution?
What is that?
F5
Like a virtualized F5 load balancer?
Yeah.
Not really. The only, the only thing that I can remember of is that we used that to test HTTP2 deployment, and that was it. I mean, we didn't do any tests with comparing the F5, the performance with the F5 virtualized environment with the NGINXs. We didn't do that. Yes.
Was there a feature you were really missing, or to rebuild it or workaround?
Not really. As I said, I mean, in our case, F5 didn't scale and didn't behave as they were supposed to. And I'm pretty sure there are people that use probably more than we did with the F5s. I mean, the features that we used with the F5s were pretty, basic. And we didn't really miss anything from the F5s. But I'm pretty sure there are people that use the F5 extensively. The thing that we had with the F5s is that as we saw a lot of increase on SSL traffic, the F5s, we upgraded a lot with the F5s, with the issues that we had with them. And at some point, they decided to drop the support for ECDSA, hardware acceleration. They moved the support of the specific cipher suites from hardware to software, and then we saw there at that point now real issues with the F5s. Yeah. More questions? I'm good. Thank you.